Hello everyone. After almost 20 years in drug discovery, I'm still convinced that the most impactful innovations come from bridging the gap between the lab bench and computational models. At BioAscent, we focus on making AI a practical tool for the everyday challenge of drug discovery. We are lucky to be part of a thriving research ecosystem in Scotland, and a core part of our mission is supporting that local science through deep academic collaborations. As we have seen recently, AI is clearly changing our field. But for it to be truly useful at the bench, it has to solve the messy practical problem we face in the lab every day. And the project that I'm going to talk about today came out of one of those collaborations where we used machine learning to solve a very real, very physical problem in assay interference. Before we dive into the data, let me give you a bit of context on BioAscent Discovery. We are based in Scotland, operating out of a former Organon MSD site, a location with a long history of pharmaceutical excellence just outside Glasgow. What makes us unique is our fully integrated approach. We bring together biology, chemistry, in silico discovery, and compound management all under one roof. This allows us to support a vast range of drug discovery projects, regardless of the modality or target class. To give you an idea of our scale, we have worked on over 20 different GPCR projects in just the last few years alone. That deep experience across diverse and challenging targets is exactly what drove us to develop the machine learning solution I'm sharing with you today. We have been working closely with several academic groups here in Scotland over the last year. Our first collaboration was with John Clark Nicholas at the University of Lincoln, now is in Strathclyde Uni in Glasgow. We used ReinVent4, which is a genetic chemistry package from AstraZeneca, molecular dynamics, and an active learning loop to design new GLP-1 receptor positive allosteric modulators. In our second collaboration with Antonia May's group at the University of Edinburgh and his PhD student Ryan Zhu, we used reinforcement learning guided by Ginina Docking to teach the model the rules of NLRP3 binding pocket and explore new chemotypes. For today's talk, I want to step away from molecular design and focus on something more practical. Instead of thinking about what to synthesize next, I want to focus on how to make the experiment more reliable. This part of work was done together with Donaldson Chuck Sokolo and the University of Stirling and looks at a very common problem in HTS, high-throughput screening, which is paints interference. By applying Bayesian optimization, we were able to identify buffer conditions that directly reduce interference at the bench. High-throughput screening is still central to drug discovery, still a major source of hits for discovery projects. But assay optimization is the bottleneck more than the screening itself. This is especially true for enzymatic assays, which are very sensitive to buffer composition and to the chemical environment around the active site. One issue in assay optimization is interference, and it can come from two sources mainly. Signal interference, when compounds can directly disrupt the readout, for example by autofluorescence, they emit their own lights, or quenching, when they block the signal, they absorb the lights, or chemical interference. Compounds can physically or chemically disrupt the environment, for instance through non-specific aggregation forming clamping, chemical reactivity when they react with the protein, or metal chelation when they chelate metals, especially in a protein binding site. Traditionally, assay optimization relies on experience, on the biology experience, biologist experience. They go in the literature, they see what others have done, trial and error, or more structured approaches like design of experiment. Even design of experiment, although powerful, in practice it becomes slow and difficult when the buffer space is large, with pH, salts, detergents, chelators, and reducing agents all interacting. One major source of a failure comes from paints. Paints means pan-assay interference compounds. Compounds that generate false signals by interfering with the assay rather than the biology, as we have seen in the previous slides. They behave like imposters, producing activity through simple physical effects such as aggregation or redox chemistry. The problem is that these artifacts look like real hits, so they get carried forward and waste a lot of time and effort. At the bottom right of the slides, we can see a typical dose response curve, where on the x-axis we have the compound concentration, and on the y-axis the activity of the enzyme. These dose response curves tell us that these compounds has an IC50 of around 10 micromolar. As soon as we add a little bit of detergent, this curve shifts and the IC50 of this compound changes. If this compound was a real heat, this shift should not happen. This means this compound is fake, is an imposter, and acting as an aggregator. Usually aggregator, what they do, they coat the enzyme, so they make the enzyme inactive. Yet pains testing is rarely built into optimization workflows from the start, and that's the gap we focus on here. Traditionally, the solution is to discard these compounds using structural fields, and me as a computational chemist have done that many times, but that's a blunt approach that risks throwing away valid chemistry. Our key insight is that interference is context dependent, so instead of deleting compounds, can we engineer buffer conditions that suppress artifacts and allow the true biology to emerge? Can we engineer using machine learning? To build a model that can see through noise, we first had to generate a specialized training dataset able to capture these failures modes in action. We use an enzymatic assay as our model system, one naturally sensitive to artifacts, to act as a benchmark. Our biologists over the years curated a library of over 153 compounds known to cause problems, such as aggregators, redox cyclers, and fluorescent interferers. The key to our data generation was environmental stress. We ran these compounds across 13 different buffer conditions, systematically varying pH, salts, and detergents. We weren't looking for perfect data. We were deliberately provoking quenching and signal distortion to show the model exactly how these artifacts manifest. This process gave us an incredibly rich dataset covering the full spectrum of behaviors, from clean, reliable inhibition to total assay failure. By generating data that explicitly highlights these red flags, we gave our ML model the grounded evidence it needs to detect and the noise interference in real-world screens. The biologists gave us a big spreadsheet with all the data that came out of that 13 different buffer condition tested for 153 compounds. And we built an automated pipeline centered around a custom load data function built in Python. This allowed us to ingest raw screening results and consolidate them with their chemical feature into a single database. We then performed what I call biological hygiene. Plate readers often produce impossible numbers like negative 3000 percentage inhibition due to technical artifacts like quenching. We clipped this to a realistic range so they wouldn't distract the model during training. We also used one-hot encoding for detergents, so the model treated them as distinct categories rather than a ranked list. Finally, we normalized all our features to ensure that variables with large units didn't accidentally dominate the model's learning process. This slide illustrates the core architecture of our model. While the diagram looks complex, the underlying logic is very simple. A compound isn't good or bad in isolation. Its behavior is a product of its environment. To solve this, we use a two-stage modeling approach. In stage one, we isolate the chemical bias. We look only at the intrinsic chemical property using radial fingerprints to predict the baseline inhibition with the spread from a molecule across all conditions. Statistically, this defines our chemical component. It tells us what part of the signal remains consistent regardless of the buffer. Next, we perform a residual analysis. This is the secret sauce of the project. By subtracting that chemical prediction from our actual observed results, we are left with what is called a residual. The residuals represent the part of the signal that chemistry alone cannot explain. It is the pure interference, the artifacts and systemic errors introduced specifically by the assay environment. In stage two, we quantify that environmental impact. We model those residuals against our buffer feature, things like pH, salt concentration, and detergent levels. By stacking these two models together, we successfully decompose a complex noise result into its two primary drivers, real chemistry versus environmental artifacts. It allowed us to finally see the biology through the noise. To ensure our results were robust, we followed a very deliberate validation workflow. First, we performed feature selection using five-fold cross-validation. This allows us to choose the optimal number of fingerprint bits and tune our parameters before we even touch the final model. Once the architecture was locked in, we trained the model on 80% of our compounds and evaluated it against a completely unseen 20% test set, a typical 80-20% split set. If you look at the scatter plot, you can see the results of that test. The model achieved a R square of 0.68, which is a very good performance for this type of noisy real-world HDS data. You'll notice the training and the text points both lie close to the identity line. The small gap between them confirms that the model is generalizing well to new chemistry and isn't just overfitting to the artifacts. Our mean absolute error is around 17%. While that might seem broad in a vacuum, for an assay with this level of baseline variability, it is highly effective precision level for guiding buffer optimization and silencing interference. Once we establish a reliable model, we need a way to find the perfect buffer. We used Bayesian optimization via Optune, which is a Python package. It can be used in scikit-learn, for instance, because it excels at navigating high-dimensional spaces that mix categorical factors like detergent type with discrete concentration. Crucially, we did not allow the AI to suggest phantom optima. Every search parameter was snapped to valid laboratory stock solution, ensuring that every recipe recommended by the code can be mixed at the bench. We chose TPE, tree structure Partisan estimator, for the optimization because it scales better than Gaussian process methods in a mixed discrete continuous spaces and performs well when evaluations are expensive and noisy, which is exactly the HTS settings. When we optimized the buffer, our goal wasn't just to minimize our error. It was to collapse the outliers. Those compounds at the far ends of the distribution are the ones that cause the most expensive false positive in the lab. We define our danger zones as anything above 30% or below 20% percentage inhibition. By specifically targeting these extremes during optimization, we achieved a massive shift. We cut the background noise by 82%, driving down from a chaotic baseline to just 17%. What does that look in practice? It allowed us to rescue 80% of our bad actors. By pulling those compounds out of the danger zones and back towards zero, we create a significantly cleaner background. For the lab, this means we aren't just seeing less noise, we are seeing more truth, ensuring that the time and money we spend on follow-ups is focused on genuine biological hits. So what was the physical drive behind this number, behind these insights? The model highlighted our standard detergents, NP40, was a major source of interference, likely forming aggregates that trapped hydrophobic compounds, masking their true activity. Based on these results, we simulated the impact of replacing NP40 with 0.02% concentration of pluronic F127. Pluronic is a non-ionic surfactant that prevents protein aggregation without the same sequestering effects, which should theoretically maintain much better compound availability. The density plot on the right here shows the predicted impact of that switch. Our model suggests we can effectively collapse the noisy blue baseline into the narrow orange peak centered at zero. By tightening this distribution, the model predicts we would achieve a near-neutral baseline of just 0.69% inhibition, successfully removing the 7.5% average bias seen in our original data. Essentially, the model is showing us a clear path to silence the buffer environment, give us high confidence that we can move forward with an assay where genuine biological activity isn't being masked by the chemistry of the buffer. Once we identify the potential optimal buffer, we tested how sensitive it is to normal laboratory variability. In real experiments, pipetting is never perfect, so we simulated a small variation in buffer composition, around 10%, which is in line with standard pipetting tolerances. The key result here is that the prediction remains stable across all these tests. This shows that the buffer represents a solid operating regime and is suitable for real experiment use. Within these realistic variation ranges, none of the individual buffer components caused a measurable loss of performance. Consistent with general enzymatic assay practice, pH and ionic strengths are still the parameter we would monitor most closely in routine lab work, but overall, the formulation is not fragile and tolerates normal experimental variability quite well. This is the moment of truth, where we took our computational recipe back to the wet lab. To provide a rigorous test, we took our library of 153 known paints compounds, which included aggregators and redox cycles, and ran them at 10 micromolar in both the original buffer and the buffer suggested by ML optimization. If you look at the x-axis on the graph on the right, the original buffer was clearly struggling. You can see several compounds classes showing mean inhibition values significantly above 30%, which are classic false positives. Now it's important to note that if our optimization had made no difference, these points would sit directly on that red diagonal identity line. But as you can see, there is a striking downward trend. The bad actors that were causing those massive false hits now sit well below the red line. This is the evidence that our ML optimized buffer successfully suppressed that false activity and tightened the data towards the neutral baseline. Importantly, we achieved this while maintaining high assay quality with a zeta prime factor above 0.6. This confirms that we haven't just muffled the signal, we have maintained a robust screening assay where the results now represent genuine biology rather than buffer-induced artifacts. It is critical to acknowledge that in assay design there is rarely a free lunch. While our optimization was highly successful, we identified a significant biological trade-off. Our kinetic analysis revealed that as we suppressed interference, we also observed a marked reduction in the overall enzyme turnover rate, or the K-cut, as people call it. Interestingly, the substrate affinity, or Km, remained entirely unaffected. This suggests the suppressive environment we engineered specifically impacts catalytic efficiency rather than the binding interaction itself. These findings provide us with a clear roadmap for future development. We must move towards multi-objective optimization models that can balance the requirement for interference suppression with the need of maintaining robust assay signal power. To wrap things up, I'd like to leave you with 3 key takeaways. First, we fixed the buffer, not the library. Instead of simply discarding problem compounds and losing potential valuable chemical matter, we optimized the environment. This ensures we aren't throwing away leads just because of buffer interference. Second, we predicted and silenced the noise. The model accurately predicted a significant cut in background interference, which validated at the bench, driving our average bias down to a near neutral 0.69%. And finally, the last point, we delivered proven success. We successfully rescued nearly 80% of bad actors compounds, proving that you can remove interference while maintaining high assay sensitivity with a zeta prime of over 0.6. Looking ahead, we see this ML approach as a scalable blueprint. By integrating these frameworks in the high-throughput workflows, we can handle the large, diverse libraries required for modern AI-driven drug design, ensuring that the data feeding the model is as clean as possible. I want to say a huge thank you to the team at BioAscent and our fantastic academic collaborators. This project is a perfect example of why bridging the gap between disciplines is so vital for modern drug discovery. Thank you all for listening. If you have any question about how we are applying these machine learning frameworks, or if you'd like to discuss a potential collaboration, please feel free to reach out to me or the BioAscent team. Thank you and ciao.